So I'm going to give you a little bit of detail about how we map the seafloor, how much of the seafloor is not mapped, which is another kind of perception challenge. The magnitude of the ocean is really hard to perceive in and of itself, and to think about how little of it we know in detail is also very difficult to understand. And I'll tell you a bit about the Seabed 2030 project as well. So first, to start off, why map the seafloor? I'm not going to read to you all these examples, but rest assured there are many, ranging from safety of navigation to ocean circulation modeling, weather modeling, marine heritage, and all kinds of resources in the ocean. So really mapping the seafloor is the basis of a lot of what we need to do in the ocean to be able to use it responsibly and navigate it safely. What surprises most people when I talk about what I do for work is that most of what we know about the shape of the sea floor is really predicted based on altimetry data from satellites. So most of what we know is not actually direct measurement of the depth of the ocean. So the way that this satellite prediction works is it's sensing the sea surface, the height of the sea surface, which actually responds in very slight ways to the shape of the seafloor. And we can, from that, model the shape of the seafloor based on gravity measurements. So the good parts of this technique is that we have a full global perspective and it's highly efficient. The cons are that it's extremely limited spatially and we have a lot of vertical inaccuracy. So there are plenty of examples where the predicted bathymetry or seafloor depth is 2 kilometers different from what we actually measure when we go out and use sound and get direct measurements. So some examples of how we can bring the seafloor into focus. Right here, we're looking at a satellite derived map of a piece of the deep sea. If we go over that same area with a ship, we can see incredible detail. Picking up on some of what Alex talked about, the way that we visualize the seafloor, we typically use a rainbow coloring, which many of my friends say makes it look like candy. It doesn't really give you a very good, solid understanding of what you're looking at. But in all the maps that I'll show you, the warmer colors typically are shallower and the cooler colors are deeper. Another way to think about this sort of lack of detail with respect to the seafloor is we've all really become accustomed to looking in our phones and at satellite data with 1 meter resolution. We can see cars in our driveways. We can see the UN building here in New York City. If we were to overlay the same kind of resolution of what satellite data for like ocean bathymetry would look like, it would look like this. So really we know very, very little and we can see very, very little of the detail. One more example, this is satellite predicted bathymetry, and here's what happens when you go and map it directly. So when we look at the global ocean, the best numbers that we have at present are that 15% maybe at best of the ocean has been mapped with direct measurement. And when we say that, we mean at roughly 100 meter resolution. So the size of a football field. You can't even resolve an airplane fully intact at that kind of detail. When you think about really detailed exploration, even less of that 15% has been explored with eyes on the seafloor. So one way I like to visualize this is this map represents the whole planet. This red box represents the 70% of the planet that is ocean, and this little blue box represents the 15% of the ocean that has been mapped. And so when you compare that to the size of the planet, it's really tiny. And so really what we should be talking about is how we don't know the shape of the surface of the planet. It's hidden by water. If we zoom into the Atlantic and part of the area that Marie Tharp really exposed for us and brought to bear, this is what our best maps of it look like now. Again, much of this is based on prediction. If I overlay a mask hiding out the predicted bathymetry, you can see just how sparse the measurements are. So how do we do this measurement? As we heard, in the old days, we used lead lines, so a weight on a line that goes over the side, and we measure the distance. We then evolved to single beam sonar, where we could effectively get a transect of depth using an echo sounder to get a profile under the vessel. Now we use what's called multi-beam sonar, which makes basically a fan of sound beams that gives us many measurements at the same time. So the way that this works, of course, is that we're using the speed of sound to compute distance. In the early days, these were profiles, like we just heard, the kinds of data that Marie Tharp worked with. As we move toward multi-beam data, there's a lot more complexities, and I'll talk to you a little bit about that in a moment. Here's just a few more examples, or some of the same ones, of Marie Tharp's work. I think one of the really important things to remember with what she did, not only was it transformative in that we had this new perspective and view on the seafloor because of these maps, but she worked with paper data. It wasn't digital. She was working with paper profiles, and she was doing all this work in an analog way. We do a lot of this now with computers and digital data, and we're still challenged with the same kinds of problems, but she did it, you know, with mathematics and an understanding of geology and paper and pencil, which is really astounding. So here's again that famous map that she published with Bruce Hazen that really first brought the Atlantic seafloor to light for us in brand new ways. So if we jump ahead to the modern mapping techniques, multi-beam sonar instruments are really the state of the art now. For the deep ocean, they're very large instruments that get mounted to the bottom of the ship. So there's a couple of pictures of those here. We effectively kind of mow the lawn. So we get these swaths of data as we go back and forth. You can see in this bottom panel on the right, and we collect as many points as we can through that, and we splice it together to make a surface or representation. Actually do have, this is actually what it looks like when we're collecting data. It's really slow and it takes a long time to get the data. But we're basically looking at the fan of sound here, and the profile of the depth is in purple along the bottom. And we use that and associate it with navigation, whoops, do some processing, and eventually render grids, which are like meshes draped over the surface, and use those to render images that lots of people can access. Well, that was supposed to be a series of things. It didn't work quite well, but the point here is once we collect this data digitally with these highly sophisticated instruments, we have to do some work to clean it up. This is an example from south of Puerto Rico, where the data that was acquired was not cleaned, and it was pushed into Google Earth. And so this pattern on the seafloor, if you can see my mouse, all these dark dots and this big dip here, those are all bad data points that were not cleaned out. And to my trained eye, it's very clear that that's the problem. I actually had an investigative reporter call me to discuss this exact place because he thought he had made a great discovery. So it's really important that as we collect this data, we take the time to clean it. I think the next slide, oh no, I didn't put it there. I had a profile that showed the messiness of this, but I didn't pull that over. So anyway, once we have this data, we bring it into fairly sophisticated software. It's joined up with navigation and the motion of the vessel, because of course we're measuring sound going through the water column. It's responding to temperature and salinity that Alex was talking about. So the speed of sound is going to change with those parameters. So we have to have very good ways of constraining that so that we get the measurements correct. And then we try to get it as good as we can, clean it up, and look at it in different views like this, and try to render this mesh to get the best model of the seafloor. So the transformation that we've gone through has really gone from these contour maps. These were the sort of pre-Marie Tharp views of the ocean bathymetry. Now here's Marie Tharp's view on top of it. And now we have the modern digital representation of the same kind of view that Marie Tharp had, supported by much, much more data. But even in this digital era with lots of data collected, we have a lot of work to do. So this top panel is the satellite predicted bathymetry here, and the bottom is measured. This is an example from the data collected in the search for the Malaysian Airlines flight MH370 that was lost in the Indian Ocean. So huge amounts of the ocean yet to be mapped. So the Nippon Foundation JEBCO Seabed 2030 project was established to really try to tackle this problem. It's being run as a joint program between the Nippon Foundation, which is a philanthropic group organization in Japan, and JEBCO, which is a project that has existed for over 100 years that operates under the joint auspices of the International Hydrographic Organization and the Intergovernmental Oceanographic Commission of UNESCO. So having those intergovernmental bodies as part of this is, I think, a very important thing. The goal of this project is to map the entire ocean by the year 2030. And the vision is to really enable policy decisions and sustainable use of the ocean and scientific research that is informed by a detailed understanding of the global seafloor. So given that 15% of the ocean only is mapped right now, you can imagine that this is a massive project. And so the project has established a regional approach. We've basically got 4 different regional centers looking after different parts of the ocean. The center that I lead at Lamont is focused on the Atlantic and Indian, which has a nice resonance with Marie Tharp's early work. So it's really nice to be able to carry that torch. And we're really trying to work with stakeholders around the world to leverage national efforts and regional efforts to drive this global effort. We're trying to bring together stakeholders from all across the maritime community. Government and academia have worked together in the past with good success, but we're really trying to bring in industry and also the public sector. Crowdsourced bathymetry is one example of the way that the public can participate. And we're really trying to figure out how to, get everyone involved to help reach this goal in a pretty short amount of time. So a couple of the things that are going to help us accelerate are new ways of acquiring data. So not just the typical sonar systems that are very expensive and installed on academic research vessels or survey vessels, but getting fishing vessels involved and private boats and tourism, and really working on the data side to really accelerate how we move data around and how we crunch it together into data products. I have 3 images here just to show you the progress that we're making in the Atlantic. So this first one is the 2014 release of the JEBCO grid. Again, black is hiding where there's only satellite data. So the blues that we see are the depth that's supported by some sort of actual measurement. This next image here is last year's release from 2019. So we've got significantly more coverage. And now this next one is the most recent release from this year. So by bringing countries together and different organizations together and uniting in purpose, we're really trying to fill in this puzzle that Marie Tharp started over 50 years ago and really try to get a much better view of the shape of the seafloor. My last slide is just to mention this exciting decade that's coming that is happening in parallel to Seabed 2030, which is the UN Decade of Ocean Science for Sustainable Development. Part of the Ocean Decade recognizes the importance of mapping the seafloor as a pillar of what it's trying to achieve. I think that coupled with that and the momentum that we have underway already with Seabed 2030, we're getting a lot of stakeholders to join us and contribute data and acquire new data. And I think the other big challenge, which comes back to diversity on some level, is really making sure that the rising tide lifts all boats, and that those of us that are fortunate enough to be in more developed countries and have better resources and more assets at our fingertips can share instruments, knowledge, techniques with countries that don't have those resources, and make sure that we all work together to complete mapping the ocean. So I will stop there. Thank you.